Good morning, Calc 1 class. Hope you all are well and hanging in there. Today we're going to start Chapter 5. Good news, this is our last chapter together in Calculus 1, so you are almost done. That is wonderful. Also, Chapter 5 will have 5 lectures. It would be really amazing if I could do 5 lectures, each with 5 parts, but I don't think we'll pull that off. We'll just have to live with 5 lectures in Chapter 5. I was going to say something, and I forgot what it was. I don't know what it was. It was important, but hopefully it'll come to me later. Okay, so the question that we're going to be looking at in Chapter 5 is very different than what we've been doing so far. So far in the class, we've been computing slopes of tangent lines. And if you think about it, that's really been our focus all the way from Chapter 2. And we spent a lot of time in Chapters 2 and 3 learning rules, derivative rules, to speed up our ability to compute slopes of tangent line. But that's what we were doing. In Chapter 4, we learned some of what those slopes of tangent lines means, what the first derivative tells you about the function, what the second derivative tells you about the function, so on and so forth. So our focus so far has been exclusively related to slopes of tangent lines. We're going to completely change the question now, or so it seems. We're going to ask ourselves how we can compute certain areas. And so we're interested in areas of shapes like this. Notice I have a function, f of x, and then I want the area under my function but above the x-axis, and I'll say between x equals a and x equals b. So this is the area that I want. And if you think about it, that's not quite clear how to do that. There's no known formula that's just going to pop the area out of that shape. Now, we know formulas for the areas of rectangles or squares or triangles or circles or so on and so forth. But we don't have a formula for areas like this. And I need a way to compute the area efficiently where I can even change f. I don't want to just do it for this function. I want to be able to do it for any continuous curve. Find the area underneath it. And so this seems very, very different than what we've been looking at, although as it turns out, there's a connection. So we're going to explore that. But for now, I want to show you some of the key ideas. So this lecture series is going to be a little bit longer because I have to set up a lot in this first lecture. But I've gone through and I've actually shortened the homework a little bit. I think I cut out 3 problems of what I usually assign just to kind of help out with the online learning thing. So we're trying to get to the bare essentials here, but I need you guys to track with the basic ideas behind this, because these will form some of the foundation for things that you'll do in Calc 2 and in Calc 3 as well. So let's try and get the basic ideas, and then we'll go from there. So our question, how do we compute area under this function above the x-axis? Well, the key idea is, let's actually write this down. So the key idea is to translate this area that we don't know and try and capture it in terms of an area that we do know. That's what mathematics is. Mathematics, again and again and again, is taking a problem that you don't know how to solve and finding a way to express it in terms of a problem that you do know how to solve. And so I'm going to think about the shapes that I just mentioned, and I think one of the easiest areas to compute is the area of a rectangle. It's just length times width. And so that's the key idea. The key idea, oops, we want to get to my pen here. The key idea is to use rectangles, and there's going to be a limit involved in it as well. We'll see that in a little bit. But if you recall, in Chapter 1 we were studying limits. I said that really calculus is limits. That's exactly what it is. It's studying the limits of different things as they tend towards infinity. So let's see how we can use limits and rectangles to get our hands on the area. So I believe I've pasted our picture already. Oh, there it is. And so here's one way we can do it. So we're going to break up the x-axis into a bunch of little pieces. We're going to assume that these little pieces are equal length. Do you see them all? And then I'm going to need to pick a point in each piece. Now you can do this randomly. We're going to practice doing it in a controlled way. So first let's pick what we're going to call the right endpoints. So I'm going to pick this point and I'm going to plug it into my function f, and I'm going to go up here. And then I'm going to form a rectangle by just going across and down. I'm going to plug in the right endpoint. I'm going to go up to my function f. I'm going to go over, form that rectangle, go up, go over. There's the rectangle. Whatever the height of your function is, when you plug in that right endpoint, you go to your function, and then that's the height of your rectangle right there. And I go there, right endpoint, plug in, go over, right endpoint, plug in, go over. And so let's observe what we've done. We have not computed the area under f. We have not done that. But we have a reasonable approximation. And what we're going to do is we're just going to start taking more and more and more rectangles. And even still, if you ever stop with only finitely many rectangles, you only have an approximation. We're going to want the precise value. But let's hold that thought for a moment. I want to show you how you can do this using left endpoints and midpoints as well. So actually, I've already got the picture copied, so let's just pop it right there. And then let's do the same thing. We're going to break it up. So 1, 2, 3, 4, 5, 6. Now let's go back and let's use left endpoint. So I'm going to plug this point in, the left endpoint of each interval, into the function, go over, form a rectangle. Then let's get my highlighter. So that's the first region, left endpoint of this piece of the x-axis. The left endpoint of this one is right there. Left endpoint, left endpoint, left endpoint. Okay, so here we go. So left endpoint, plug it in, go up, go over. Left endpoint, plug it in, go up, go over. Left endpoint, plug it in, go up, go over. You get the idea. Left endpoint, left endpoint, left endpoint. So you can see that these are actually different estimates. We're not going to get exactly the same, but they're both estimating. You can actually do this if you wanted to with midpoints. So I don't want to spend too long on this, but you can, if we break this up like this, you could actually plug in the midpoint of each one. So plug in the midpoint of this piece, go up and form a rectangle. Plug in the midpoint of that one, go up, form a rectangle. I kind of like the midpoints. Form a rectangle, just going up, plugging in the midpoint, and I shouldn't have drawn that line. That's going to make you think it's, oh shoot, part of the square there. Yeah, I think it's stuck. Oh well. There we go. So left endpoint, oops, it's a disaster. Not left endpoint, midpoint, plug it in, go up, that's your height. Midpoint, plug it in, go up, that's your height. Midpoint, plug it in, go up, and so on and so forth. So you can plug in midpoints. You can actually do it randomly. You can pick a point. Let's just do it in red. You could have picked this point for that one, and then this point for this rectangle, so on and so forth, and do it randomly as well. So that's the basic idea. I'll stop this video here just because we're getting a little bit long, and then we're going to work through an example video problem in the next video.